So let me start right away. We saw last time that if we are given a set, so this was, if you have a set of vectors, you have a number of them. So let's call that we have n of them. And if I make linear combinations, of these vectors, that means I'm looking at vectors of this form. I hope people can hear me on the other side. So these are vectors from a vector space. So if I make a linear combination, I still get a vector back in my vector space. So these are originally from a space V, and W is just a finite subset of V. I have a vector space V. This is a vector space. And I picked n vectors from there to make this set W. So picking those n vectors, if I make any linear combination, since V is a vector space, this linear combination which I will make will mean that this V also belongs to the vector space. This is obvious. This is like the main point of having a vector space. But we saw something more, that if I consider the span of W, that means all vectors of this kind. You choose all values, all possible values for these alphas, these constants. Not just one particular one, but all of them. And these alpha I, you consider all of them. And you collect all these vectors. So when you collect all these vectors, this will be this span, this new set which you will create, the span of W, since you are getting back vectors from the vector space, is still a subset of V, but it's more than that. It will be also a subspace. That means this set in itself will be a vector space. Or, in other words, span of W is itself a vector space. So our starting example where we got this idea was that we had a matrix, this matrix, and we were looking for the null space, that all those vectors, those 4 component vectors which solve this equation, the homogeneous equation. And we found that the null space of A is spanned by so they were all vectors of this form. A, B, are completely arbitrary. Now you can consider in other spaces, in other vector spaces, pick up some set of vectors and consider their span. So I guess this example we considered last time as well, but let's just look at again. So I pick two vectors from R3, from vector space of column vectors of this form. Now I make a span. Let's call it some set W. Are these guys. Where A, B are any real numbers. So all vectors of this form. And these will be, if I compute it, will be vectors of this form. And we saw last time that if you have a zero down there, one of the components you fix to zero, then these guys, this is a subspace. Well, let's quickly check. This space, which we have found, vectors of this form, where A, B are any arbitrary constants, it's a subspace. Just a reminder, how do you check if it's a subspace or not? You pick two arbitrary elements from this space, from this set. So let's take, this is one arbitrary element, completely any value for the first component A and the second component B, which I am calling A1 and B1, and completely arbitrary values for the second vector, and I multiply them with arbitrary numbers. Let's call it alpha 1 and beta 1. So what do I get? I get alpha 1 A1, alpha 2 B1, 0, plus alpha 2 A2 plus alpha 3 A3. So I do get a vector of the form which are present in span of W. So this is in span of W, and that's enough to show that span of W is a subspace of R3. So we have seen these two examples that if I pick any number of vectors and make a span, I am getting a subspace. So you can, well, let's take one more example. This time let's consider R2, and let's take these two vectors from R2 and make a span. So span of this W is of this form. AB arbitrary, but that is just the complete R2 back. So span of W is R2. So our suspicion that whenever I make a span, I get a subspace is being fulfilled over here. But this subspace in this case is the whole space itself. That can happen. Now, so this suspicion, we can put it in the form of a theorem to confirm that it always happens. The span of any number of vectors where these v1, v2 are from any vector space is a subspace. So the proof is completely trivial. You just have to pick any two vectors from the span. So what are the typical vectors in the span? This is one vector. This is another vector, completely arbitrary. Choose any real numbers in front and you get a new element from the span. And I have to multiply them by some constants, let's call alpha and beta, and add and check if I get something back from my original set or not. So when I do this, I can collect the coefficients of V1 similarly collect the coefficients of V2, so on. But these are just again numbers. And in my span, I have all linear combinations of these vectors v1, v2 to v3 and to vn. So this does belong to the span of this set. So that means we have proved that the span of any number of vectors, this n was completely arbitrary, is always a subspace. Then we had this concept. I think this is also we discussed last time, but it's just a repetition from last time so far. The spanning set. So now you are turning around this logic because you know that if you pick any number of vectors and span them, make all linear combinations, you're going to get some vector space. Typically, it would be a subset, a subspace of your original space. So I can ask if I'm given a subspace of a vector space or the vector space itself, can I find some vectors which will span it so that if I make a span of those vectors, I get my space back. This is called the spanning set of V. So if span of a number of vectors is V, then the set is spanning set for V. So what are the examples? If you consider the three-dimensional space, the geometric vectors, then I, j, k, what you call the unit vectors, I here, j here, k here. Since you know that you can write any vector over here like this. So this is a spanning set for the space of geometric vectors. Another example for the, well, let's consider this example. Consider this set. The question is this a spanning set for R2? These are vectors from each one of them, from each vector here is from R2, right? This is of the form AB. The question is the span of these vectors R2, is this a spanning set for R2? So for that, we have to check. We can make, how do we check? I make the span, a typical element will be this. I can choose any B, any A, B, C, any constants over here. And using these, I should be able to make any vector of R2. So you are given, you pick alpha and beta of your choice, two numbers of your choice. So since you are keeping them completely arbitrary, you're considering all vectors in R2, and you are trying to see if I can choose A, B, C, and D, because any value of A, B, C, and D will be in the span. That's the definition of span. Can you do it? Well, this is equal to this is this vector, and you are putting it equal to this vector. So you are trying to solve this equation. So if I add this below, this goes to zero, 1, 2, 0, alpha plus beta. And now I'm bringing it to reduced row echelon form. So this becomes, I add it above. So when you add it above, you have to multiply it with a -1 and then add it above. You get 0, -1, -1, minus alpha minus beta added above gives you minus beta. So what you see is you get C and D are free variable, and A is equal to minus beta plus C plus D, and B is equal to alpha plus beta minus 2C. So that means you're given, you wanted to create any vector with alpha and beta, arbitrary alpha and beta. You pick those alpha and beta, you can keep C and D anything you like. And you can compute what A and B you need. But all of these are available to you. So you will be able to make linear combinations which give you alpha and beta. Well, actually, not one linear combination. You have huge number of linear combinations which creates for you the vector alpha beta. So that means this starting set was a spanning set for R2 because I can write any vector in R2 as a linear combination of this set. So in words, you can say a spanning set, well, if you can write any vector from a vector space V as a linear combination of a fixed set of vectors from V, then that fixed set is the spanning set. So in a sense, you just need those sets, and just by making linear combination, you get the everything else back. So in this spanning set, this particular one which I just chose, let me consider this vector. What I notice is, so let me just write the set here again. This was my set. So this one, this guy, I can actually write it like this. So that means this guy is itself made up of two other elements of the sets. Other vectors of the spanning set. What would that imply? That would mean that if I write any vector V as this kind of a linear combination, I can replace this vector 1 minus 1 by this one. So I will have 2A 1 0 minus A 1 1, and then these guys, 1 minus, this was 1 plus 1. Plus C 1 0 plus D minus 1 1. So now I can collect these. B minus A 1 1 plus D minus 1 1. That means first I established that I can write any vector of R2 as a span of these four vectors. But then I found that one of them is actually can be written in terms of two other members of this set. So whenever I make a linear combination, I can replace this guy, this one, by that linear combination which makes it up. So finally, what turns out, I can as well make any vector in R2 in terms of these three. So since this guy is made up of these three, I don't need it if I want to construct my R2. Those three will do the job as well. So I can delete it and I will still have a spanning set because it's made up of other two. But similarly, now I look at this guy. This is equal to so I had deleted this one and my spanning set, new spanning set was now 1 1 1 0 and minus 1 1. But over here, I again realize that one of them is actually a linear combination of the other two. So again, any linear combination of which I write of these three vectors, I can replace this guy in that linear combination with a combination of these two. And finally, I can write any vector as a linear combination of only these two. Again, because I can write this guy as a linear combination of the other two. So I can again delete. Now the question is, so that means my spanning set reduces to these two. We can very quickly check that, well, first of all, can I delete one more? So suppose, first of all, to do that, I will have to check, can I write 1 0, for example, as some, or 1 1 as a sum combination of 1 0? I can't, because all I can do, I'm given only this guy, I can multiply it with some number, let's say C, but that's just gonna give me C0 over here. I will never be able to change this 0 right here. Similarly, the other way around. So one of them, they cannot be written in terms of each other. So you say kind of that they are independent vectors. One cannot be written in terms of the other. So that means first of all, if this is a spanning set, I should not be able to delete anything from here. And this you can easily check. If I'm giving any element A, B, or let's say alpha, beta of R2, we can quickly check that it is indeed a spanning set, because we can choose alpha is equal to, this gives us these equations. So I'm given a beta, I have to choose, I'm given alpha and beta, I have to choose A and B so that I construct this vector over here. How do I choose it? From these equations, I see that I put A equal to beta, and then I put B equal to alpha minus A. I had found A and I was given alpha, so I can find B as well. So I can find A and B, which will construct for me any vector alpha beta in R2. So indeed, this set is a spanning set. But I cannot write any alpha beta in terms of any one of them. This is just this vector. This vector will have both components equal, and my arbitrary elements in R2 do not have equal components. So this is not good enough. So I need these two guys. Yeah. You have to speak really up. It's very, very loud over here. I just did not hear you. It was still a spanning set. So when we had 4, so the idea, what we discovered, that we were given a spanning set. And by chance it had 4 elements. But we found just by inspection that it is a spanning set, but it has more information than we need. Kind of, we can get rid of one of the vectors over there and we will still have a spanning set. So the idea is we are moving towards this idea that we will be looking for the minimal possible spanning set. So we were given 4, but we found that one of them can be written in terms of the other 3. And then we got 3, but then we again found that actually it's still more than what we need. Another one can be written in terms of the other 2. So we deleted that too. And once we were left with 2, we found we cannot delete anymore. These 2 are needed. If we get rid of any more, we won't have a spanning set. So you start with a spanning set and you start deleting until you have the minimal possible spanning set. But so let's start from this guy. So we had deleted this element. This was deleted because we saw that it can be written as a linear combination of the other 2. But what about if I look at this guy? This can be written as a linear combination of these 2. Right? Yeah, this works out. So that means this one, which we had deleted before, wasn't special. Actually, this guy 1 0 could be written in terms of the other 2. Similarly, this guy can be written in terms of 2 plus 1. Yeah, this works out. Similarly, the first one can also be written in terms of the other 2. So I could delete any one of them and retain the other two. So for example, if I delete this guy, then I'm left with 1, 1 and minus 1, 1. And if I make a linear combination of them, I have, so I can easily solve it. I'm given alpha and beta, I can solve it and get A and B. One thing you should notice more is that the A and B I get in this linear combination over here, they are turning out to be unique this time when we go to this minimal possible set. Before, when we had 4, we had many possibilities. But then we started deleting and came down to the minimal possible number, which will generate my vector space. Then this became unique. So this will turn out to be actually a theorem. Similarly, I can do it with deleting this guy and retaining the other two. And you can very easily check. They will also be a span. So actually, the right way to think is not that one of them is composed of the other two. The right way to think of them is that these three are dependent on each other. So any one of them you can write in terms of the other. So what we have learned over here in this example, we can summarize it in these observations, which will turn out to be true for all vector spaces. So first of all, the first thing which we have noticed that if you are given, we did it for an example, but this is true for any number of vectors from any vector space. Spans a vector space V, and one of them can be written as a linear combination of the others. Then the rest still span B. So if one of them, this is what we found, can be written as a linear combination, you can delete it and the rest of them will still form the vector space. And how do you know that one of them can be written in terms of the others? Well, and because we observed that this is not usually, it's not something special about one of them. It's usually about their interdependence. That if you are given, and this color is not very nice. For any n vectors in a vector space V, any vector space, not any particular one of them can be written as linear combination of others if and only if this holds. That the linear combination is 0 for all Ci not 0. With not all Ci is equal to 0. Because if you pick any number of vectors and you pick the constants to be 0 in front of the linear combination, then any number of vectors give you a 0. So if you have a non-trivial combination, that you can make a 0 with at least one of them non-zero, then you will have the property that one of them can be written in terms of the others. So this is like a test. We want to delete, and how do we know that we can delete? How do we know that we can write one in terms of the others? By checking through this. So how do we know that these properties are true? Proofs are again extremely simple. So suppose one of them can be written in terms of the others. So let's call that to be the nth one. I just number it the nth. Then you will be left with, let's call it not A, let's call it B, some particular constants. You can write one of them in terms of the other. Suppose Vn is the one which can be written in terms of the others. That means that this will happen. Then any vector v, since our original vector span is this one, I can replace. It will be so my any vector would turn out to be a linear combination So I will be able to write, because one of them is just a linear combination of the others. I can collect the coefficients and I will be able to write any vector in terms of the rest. So that means the rest still span the vector space. And how do you prove the other? Well, that's a if and only if statement. So if one of them can be written as a linear combination of the others, then, so suppose again, this is the Vn. It's still completely general. Whatever can be written, I'm just numbering it n. This is just an index. So all I have to do is take it to the other side. Or if you're going by the postulates, you're adding minus Vn on both sides. So at least one of them, actually at least two of them are not zero. One of them explicitly over here, at least one of them is not zero. So you have proved that if one vector can be written in terms of the others from a set of n vectors, then the linear combination, you can make a linear combination of them to make a zero vector with at least one coefficient not equal to zero. And on the other hand, if you are given this is zero with at least one not equal to zero, so suppose the one which is not equal to zero, you can call it anything. I'm gonna call it an. You can pick the jth one, anyone. So suppose an is not equal to zero, then you can write multiply add to the both sides minus a and vn. And then divide by an. So now you see that this was extremely important that one of them was not zero, because if an was zero, you couldn't divide by an. And so on. So you have proved that you can then write one of them as a linear combination of the other. So this is a test to check if they are linear combinations of each other or not. So this property that when you can write one in terms of the other, and as we saw, that is not usually a property of one particular one. It's just an interdependence of those sets of vectors. This is called the linear independence. If n vectors are linearly independent, or well, let's say n vectors are called linearly independent, so you pick n number of vectors from a vector space. If this holds, ये जो भी आपने प्रूफ किया था, if this holds, only if you're given this implies that all of these guys are zero. That would mean that these n vectors are, then you will call them, they are linearly independent. And why is it important? Because once you know that they are linearly independent, you know that none of them can be written in terms of the others. So if you are given, for example, a spanning set, and you know that it's linearly independent, these vectors in the spanning set are linearly independent, you know that you cannot delete anymore. Otherwise, you call them they are linearly dependent. That means you make this linear combination of these vectors, get a zero, and you know that you have a solution where not all of these ci's are zero, then they are dependent. Then one of them, at least one of them, can be written in terms of the other. So we can take examples. So if I consider these vectors, and I have to check, are they linearly independent? So how do you check? You make a linear combination and put it equal to the zero vector, which for this vector space is 0, 0. So that means you have a plus c and b plus c is equal to 0, 0. And this guy has uh, very trivial solution, non-trivial solution. So you pick any C and put A and B equal to minus of that. So A is equal to minus C, B is equal to minus C, and A, B, C, none of them are zero. So you can find constants which will make a linear combination which is equal to zero. So that means these are linearly dependent. They're not linearly independent. On the other hand, if I consider these two, then I have linear combination is a b and I'm putting it equal to 0, 0. That's only possible if a is 0 and b is 0. So the two coefficients coming in the linear combination have to be 0 for this to be 0. This implies that these guys are linearly independent. Similarly, you can check these. If I take this one, I can't hear you. Can you speak?
I'm saying the general rule is that these variables have to equal zero, right?
Yeah. The variable, you have to put the linear combination equal to 0, and then the coefficients have to be 0. That should be the only possibility to make a zero vector. So again, as I said, that it's a property of the set, not of one particular element usually. So I pick 1001, now I pick 10 and this other guy, 11. Now let's check if these two are linearly independent or not. So this implies that this is 0, but that means b is 0 and a plus b is 0. But if b is 0, then a plus b is 0 implies a is 0. So again, you got that both a and b have to be 0. So that means these two are also linearly independent among themselves. You can take, let's take an example from R3. 1, 1, 1. Let me make it a little easier. Let's consider these three. So you again check a linear combination and put it equal to the zero vector. So zero vector takes different forms in different vector spaces. Property is that you add it to any vector, the vector comes back. So you get A plus B and A plus C and A. So you can easily see this implies A is 0, but then the above equations imply B and C are also 0. Only possible if A, B, and C are all 0. So they are linearly independent. What if you are given, well, this was easy to solve. In general, what would happen? If you want to check the linear independence, let me write a nice theorem. Be n vectors in Rn. I'm not talking about any general vector space. You have the Rn space, and from that, you're picking exactly n number of vectors. Then construct this matrix. You can recall that I can make matrix by collecting the columns. Since each vector over here is, these are elements of Rn, so they are n component vectors. So I've collected n vectors, each one of them having n components. So this is a n by n matrix. Then this guy, this is equal to what? It will have non-trivial solutions. We know how, when it's going to have non-trivial solution. If and only if x is singular. Because if your x is not singular, I can multiply both sides by x inverse, and that will imply that necessarily this equation has only one solution, which is c is equal to 0. But what is this equation saying? Remember, we decided matrix multiplication with vectors in many ways. One of them was that you make linear combination of this vector. So this was equal to, you take the vectors, column vectors in X and make linear combinations with the components of C. And this I am putting equal to the 0 vector. And my theorem tells me that this was that if and only if x is singular, then I will have that C can be 0. So I can check if these n vectors are linearly independent or not. They will be linearly independent if and only if their matrix, if I form it this way, is singular. So you just create the determinant and check if the determinant is 0, then they can be linearly independent, not otherwise. So this will have non-trivial solutions. Solutions if and only if x is singular. But that would imply that these vectors are linearly dependent. Non-trivial solution means, because it's a homogeneous equation, you always have a solution where you put the coefficients equal to 0. If x is non-singular, if x is singular, then you will also have non-trivial solutions, which will imply that the vectors are linearly dependent. So for linear independence, determinant of x must be, so x must be singular, non-singular, that of x is not equal to 0. So for example, if you want to check if these three vectors in R3, since I'm in R3 and I'm given three vectors, if I want to check if they are linearly independent, all I have to do is compute the determinant of this. And if this is not equal to 0, then they will be linearly independent. Now suppose you are given more different number of vectors than the dimension of Rn. So we are in R4, vector space is R4, but you are only given three vectors. So then you cannot use the determinant. Now what you are doing is you are multiplying this with A1, A2, A3, and putting it equal to something like that. So in a sense, you have three unknowns and four equations. So all you have to do is make the matrix of it and find its row echelon form. So the row echelon form of this one, I'm just writing the answer. The left hand side, nothing happens to it because it's made of zeros. The row echelon form of this guy has one free variable. That means I can choose it to be anything. And that would be a sign that I have a non-trivial solution. if it were something like this, then when I will create then I have no free variable. Then when I create the reduced row echelon form, I will be making zeros upstairs, and all three variables will turn out to be zeros. So if you have free variables, then you don't have linear independence. Maybe I should give you a little bit of geometric intuition. So as I talked about last time, elements of R2, they are called R2 because you can plot them in plane. So the first number, think of it as the x coordinate, and the second number, think of it as the y coordinate. And B is y coordinate. So for example, if I write 1, 2, it's over here. And if I write 2 minus 3, it's over here. So you can make vectors from origin to the point which describes these two numbers. And then the rules of vector addition just translate that you add the components, just like we have been doing. And you can scale these vectors, change their length by multiplying by numbers. So if I consider this guy, or maybe let's say this guy, 1, 1, and 3, 3, and 5, 5. Well, if you consider any object of this kind, any vector of this kind, is just a multiple of 1, 1. That means these ones, this and this, are linearly dependent. But how do they look on this plane? 1, 1 is this guy. AA is, I pick any arbitrary value of this x and any arbitrary value of y, and the y has to be the same. So it's along the same line. So that means these are linearly dependent in R2 if they lie along the same line. On the other hand, if I pick any of these, like for example, 1, 0, they will not be linearly independent. So if I pick a vector like this, and then this vector, then they are not linearly independent, because I will never be able to make a 0 by a combination of these, right? Because they have different x and y components. You can try doing it head and tail rule. It's quite obvious. Intuitively, we have seen that you cannot do it using these numbers, but intuitively it's also clear that you can never make, by scaling them and adding them, you can never make a 0 out of these two. So these are linearly independent. If I consider R3, so I have this axis as well, z-axis. Now, if I consider one vector here and one vector here, in xy plane. The both vectors lie in xy plane. If I make their linear combinations, I'll get a vector again by head to tail rule. If I can extend it like this, I can reduce its size by scaling. Whatever I do, I'll get a vector in R2. I will not be generating any components along R3. So that means if I have two linearly independent vectors, they generate a plane, they can make a plane, they can span a plane. But if I throw in the third one in the same plane, it will be linearly dependent. So three vectors in a plane will always be linearly dependent. While if I put another vector which is out of the plane, so let's say going a little bit in this direction, but going a little bit in the z direction as well, then that one will become linearly independent combined with the two vectors in xy plane. Because I will not be able to kill its component along the z-axis by a linear combination. And if I consider a span, so I talked about I and j. We know that I can make any vector in the plane, in the xy plane, as a linear combination of I and j. I hope everyone has seen these unit vectors, I and j. And if I throw in a third vector, which is some particular linear combination C1i plus C2j, clearly I can write j as x over C2 plus C1i over C2. So that means j, then these three are linearly dependent. X, Ci and C, X, I and j are linearly dependent because X was composed of I and j. And I can, if I want, I can delete j and take X and I to be my generators of the spanning set. X and I to be the spanning set. I can make anything which I was making with I and j with X and I. Because whatever I made with j, I have to just replace this j with C2i. So I and any other vector will do the job. Well, actually, I can take another one. And now replace I as well. So I will be able to write any vector in plane in terms of x and y. So I and j have nothing special, just as we saw in our examples. They are just two linearly independent vectors, and we should be able to do it with two other linearly independent vectors. There's one caveat in this logic. When will I fail? So forget about this y for now. What I did above this line will fail in one case. Can you point out? Yeah, if C2 is 0, then I won't be able to divide and this whole logic will fail. So that means this x must not be collinear with I. It should not be just the scaling of the I vector. It has to point in some other direction. That will make it linearly independent of I. Similarly, if I take this y, it has to point in a different direction compared to x. So geometric intuition is that if you are in a plane, two vectors, they form a plane if they don't point in same direction. And any two vectors in a plane, as long as they don't point in same direction, they are linearly independent. But if they are pointing in same direction, then the one is just a multiple of the other. It's just the scaling of the other. So we shouldn't think of it as completely independent. One can be got from the other. And once you have two vectors in a plane, you throw in a third one. you can always make it by using head to tail rule of the first two. And if you go into 3 dimensions, then uh, you have 3 vectors can be linearly independent. But if they all lie in the same plane, then they are linearly dependent. So line is replaced with a plane. 3 vectors in same plane are linearly dependent. But if you take 2 vectors, they form a plane. You add a third one which is not in the same plane, then these 3 will be linearly independent. So let's stop here.